So finally, what we're going to do is to be able to calculate equilibrium concentrations, and we only might know the initial concentration. So once we know what the K constant is, we can use it to find equilibrium mixtures in lots of different cases. All right, so let's go back. This is an equation that we saw before. CO plus 3H2 gives us CH4 plus H2O. Suppose we have a mixture that contains 0.3 moles of CO, 0.1 mole of H2, 0.02 moles of H2O, and we don't know how much CH4 it is, but we know that it's at equilibrium. So how can we figure out how much CH4 there is? Well, as long as we know the K value, we can do it. So the Kc equals 3.92, and so let's plug that in. So we know the K, okay, be careful, like I said, to first divide by the volume. In this case, that's 1 liter, so that's not too hard. 0.3 molar CO, 0.1 molar H2, 0.02 molar H2O, and we want to know what is the CH4. Since we know the Kc expression, we can plug in what we know. We know the Kc, we know H2O, CO, H2. So 3.92 equals CH4 times 0.02 divided by 0.3 divided by 0.1 cubed. So if we solve for CH4, we get 0.059. So again, because it always goes to that same set point, we can find the equilibrium concentration of any of the others as long as we know the K value and all the others. We can find the one that we're missing. All right, but what if we start a reaction with known amounts of starting materials, but we don't know anything else? We want to know what the quantities at equilibrium will be. So what we're going to do, this is going back to that ice chart. We're going to use that ice chart to solve our problem. So let's look at this equilibrium. This one's a little bit different from the last one. CO plus H2O gives us CO2 plus H2. Suppose we start with 1 mole each of CO and H2O in a 50-liter container. What will the concentration be at equilibrium at 1,000 degrees? The temperature is not important as long as you know the K value at that temperature. The K for this reaction at 1,000 degrees Celsius is 0.58. So we know the K value, we know the initial concentration of CO and the initial concentration of H2O, but that's all we know. And what we want to know is the concentration of each substance at equilibrium. So again, we're going to bring our ice chart into it. So first, start out by calculating the molarities of what we know. Since we know it's 1 mole in 50 liters, do that. What are the concentrations of CO2 and H2O? Well, they're 0. We haven't put any in there. So this is not at equilibrium yet, but these are the concentrations that we've mixed together to start with. So we've put the CO and the H2O in, but we have no CO2 and H2. So since it's not at equilibrium, first of all, if you tried to plug this in the Q value, you would see, oh yeah, it's not at equilibrium because it's 0 and equilibrium is not 0. It does have to go to the right to try to form products. And so let's set up this ice chart and you can see what I'm going to do. So we set up this ice chart where it's initial change in equilibrium. So here we have our initial 0.02 molar, 0.02 molar, 0, 0. Now, what we do know, we don't know how much of CO is going to react. We don't know how much H2O is going to react. We don't know how much CO2 or H2 will be produced, but we do know how they're related to each other. So this is a nice simple one because everything has a 1 for a coefficient. So if we lose one CO, we will also lose 1 H2O. We will gain 1 CO2 and we will gain 1 H2O. So we don't know how many we're going to lose or gain, but we'll call that amount X. So if we lose X amount of CO, we're also going to lose X amount of H2O. It means we're also going to gain X amount of CO2 and we're going to gain X amount of H2. So the change is always how things are going to shift, and it's always related by stoichiometry. So that means at equilibrium, we have 0.02, what we started with, minus whatever reacted, so 0.02 minus x. We have the same thing for H2O, 0.02 minus x. The amount of CO we have is x, and the amount of, CO2 we have is x, and the amount of H2 is x. So if we plug that into our expression, there's Kc, CO2 times H2O, so that'd be x squared, and then CO times H2O in the denominator, that'd be 0.020 minus x squared. So here's our expression, 0.58 equals x squared over 0.02 minus x quantity squared. So now we can solve, we have an equation with one unknown. Rather than 4 different unknowns, we have one unknown x. So we can solve this equation. So 0.58 equals x squared over 0.02 minus x quantity squared. We can solve that quadratically, but we can also see that this is a perfect square on the right. So if we take the square root of both sides, the square root of 0.58 gives us 0.76. The square root of x squared over 0.02 minus x quantity squared gives us x over 0.02 minus x. So now we multiply both sides by 0.02 minus x. So we have 0.76 times 0.02 minus x equals x. We have to distribute the point. So when you multiply both sides by 0.022 minus x, you get the first equation on the left, 0.0200 minus x quantity times 0.76 equals x. And then if you distribute that 0.76, so you get 0.0200 times 0.76 minus 0.76x equals x. Then if we bring all the like terms on the same side, so we have 0.0200 times 0.76 equals 1.76x. And then if we divide both sides by 1.76, then we get x, which is 0.0086. So now we can plug that x back into our equilibrium values. So now all you have to do is take the x value that you got, which is 0.0086, and plug it back into the equilibrium line for x. So our two reactants, which are both 0.0200 minus x, if you plug in 0.0086, you will get 0.0114. So both the CO and the H2O are 0.0114 molar, and then both the CO2 and the H2, since they're just equal to x, will be equal to 0.0086, both of them. One thing that you might want to do at this point, just to check yourself, take those values and plug them back into the K expression. So in this case, it would be CO2 times H2 divided by CO divided by H2O. So in this case, it would be 0.0086 times 0.0086 divided by 0.0114 divided by 0.0114. And if you plug those numbers in, you get that equal to 0.57, which is really close to our original K value of 0.58. You're not going to get usually the exact number because of rounding errors and things like that, but if you come pretty close to it, then you know that you solved this problem correctly. So the preceding example kind of tells you the 3 steps that you're going to go through for calculating equilibrium concentrations. The first thing you're going to do is set up your table, your ICE table, the initial change in equilibrium expressions. So you want to make sure, for the most part, if it tells you a volume, you want to make sure and take the moles divided by the volume before you set up your table. So set up a table of concentration for each of the reactants and products. Then what you're going to do is substitute each of those into the K value, into the K expression. So you have you're given the K value, and you know your products divided by reactants raised to their coefficients. So you're going to plug those expressions in. Unfortunately, then you have to rearrange the equation to solve for X. So you're going to solve that equilibrium constant equation. You're going to find the value of X, and then you're going to take X and plug it back in into your concentrations from the table, and then you'll get what your final your equilibrium concentrations are. And you may not be thrilled to hear this, but in some cases it might be necessary to solve the quadratic equation. And so you want to get your math skills out of mothballs and sharpen them up a little bit to remember how to solve using the quadratic equation. It's a lot easier than it was in my day, because you can often, what you need to do is rearrange the equation in terms of ax squared plus bx plus c, and then use your a, b, and c to plug into the quadratic equation. And so the next example will show you how to solve that. Okay, so let's look at this example. Consider the following equilibrium. H2 plus I2 gives us 2HI. So suppose 1 mole of H2 and 2 moles of I2 are placed in a 1 liter vessel. How many moles per liter, what molarity of each substance are in the gaseous mixture when it comes to equilibrium at 458 degrees Celsius? The Kc at this temperature is 49.7. So I do want to point out something. So a lot of times they give you a lot of extra information, and you know, what does it matter that it's at 480 degrees Celsius or 458 degrees Celsius? Well, it doesn't really matter. But the fact that the K can change at different temperatures is important. And so they're telling you that this is at this temperature, the K value is 49.7. So the temperature is not really important, but the K value, of course, is. So we have 1 mole of H2, 2 moles of I2. They're all in 1 liter, so it's 1 molar, 2 molar. There's no HI yet, so that's 0. All right, the H2 will decrease by X. The I2 will decrease by X. The HI will increase by 2X. And so at equilibrium, we'll have 1 minus X for H2, 2 minus X for I2, and 2X for HI. So now if we plug it into our equation, and don't forget the HI is squared, so we plug that in, we get 2x quantity squared. One of the biggest mistakes is people forget to square that 2. So 2x quantity squared is 4x squared. Don't forget that. And then we have in the denominator 1 minus x times the quantity 2 minus x. So what we have to do is rearrange this to solve for x, and it's a quadratic, so it's going to take a little bit of work. Because the right side of the equation is not a perfect square, we have to solve the quadratic equation. All right, so the first thing you want to do is bring everything over. You see that I multiplied the 1.0 minus x and 2.0 minus x. We multiplied both sides by that, and then I squared out the 2x quantity squared becomes 4x squared. So here's our equation. There's a couple of ways that you can do it. Note that we're going to have to distribute. Remember, we have to multiply 1 minus x times 2 minus x. Remember how to do that using the FOIL method. 1 times 2 minus 2x minus another x, and then finally plus x squared. So using the FOIL method. Then you're going to have to take that and multiply everything by 49.7. An easier way to do that would be to take, at this point, divide both sides by 49.7. Okay, so what's happened here is I divided both sides by 49.7. So 4 divided by 49.7 gives us 0.080 x squared. And then we expand the left-hand side. So again, 2 times 1 is 2. Negative 2x plus another negative x gives us minus 3x. And then negative x times negative x gives us plus x squared. So we have this expression. We want to get all the terms on the same side equal to 0. So what I'm going to do is I'm going to subtract 0.080 from both sides, 0.080 x squared from both sides. So once you subtract the 0.080 from 1, we get 0.92 x squared minus 3x plus 2 equals 0. And this is, we remember that we want to rearrange it this way so that we have our x squared first, our x next, and our no x term last, because then we can line them up with a, b, and c. So we know that a equals 0.920, b is -3, don't forget that negative, c is 2. So now we can plug that in our quadratic equation, which is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Some of you may have calculators that can do this very easily. Otherwise, you're going to have to plug it in. So, -3 squared minus 4 times 0.92 times 2. Take that whole quantity, take the square root, take negative b, which would be 3, plus or minus that quantity, and then divide it by 2a. And what do we come up with? We end up with x equals 2.33 and x equals 0.93. So these are the two possible solutions to the quadratic equation. Now, which one should we pick? Well, we need to pick the one that will make sense for this equation. There's only going to be one answer. If we picked x equals to 2.33, you would notice that we're going to have negative concentrations, which of course solves the math problem very nicely, but doesn't really make any sense for a real life problem. So we're going to ignore 2.33, and we know that our answer is going to be x equals 0.93. So now we can plug that 0.93 back into our equilibrium expression, and we find out that 1 minus 0.93, oh, there we go, 0.93 works. So again, we plug that in, and 1 minus 0.93 gives us 0.07 H2. 2 minus 0.93 gives us 1.07 of I2, and then 2 times 0.93 gives us 1.86. And again, if you plug those numbers in to the equilibrium expression, you take 1.86 squared divided by 1.07 divided by 0.07, and you get 46, which is really close to the original. Again, there's some rounding errors, but it's really close to the original K value. So you know that you probably solved this pretty well. All right, Le Chatelier's principle. Usually the goal of a chemical reaction is to get as much possible product as you can. So that's where this is coming from. Obtaining the maximum amount of product from a reaction depends on the reaction conditions. So we've been talking about equilibrium, and we know that the reaction kind of comes to it's not actually a stop, but the rate of the forward reaction and the rate of the reverse reaction are equal, and so it looks like the reaction has stopped. So you can't really make any more product when it gets to that point of view. Well, Le Chatelier's principle is, Le Chatelier was the person who looked into it. He said that when a system is in a chemical equilibrium and then it's disturbed by some kind of change, either temperature or pressure or concentration, the equilibrium will shift in a way that tends to counteract this change. Okay, so let's refer back to the U tube that we looked at the very beginning of this chapter. If we can think of the left-hand side as our reactants and the right-hand side as our products. So let's think about removing a product. All right, well, if we remove a product, so you can think of it as either maybe taking an eyedropper and sucking up some of the product, or scooping it out of the right-hand side of the tube. Well, what would happen? Eventually, all the liquid would shift to the right. It would balance itself back out, right? The whole tube of water would shift to the right to try to replace what was left. In the same way, if we add some more reactant, so if we took some and poured it in the left-hand side, again, what would happen, it would be out of balance for a minute, but then it would shift to the right again to try to rebalance. So it would shift to the right. So to shift something to the right-hand side of a product, to the right-hand side of a reaction to form products, we can do one of two things. We can increase the amount of reactants, so like increase the concentration of a reactant will produce more products. or remove some of the product. And this is actually how many manufacturers, if it's not a very good reaction and you can't make a lot of product, what they'll do is they'll continually remove it. If you do that, the equilibrium will keep shifting to the right and you'll keep producing more and more products. So to shift to the right, we can either increase the concentration of reactants or decrease the concentration of products. The same thing would happen if you want to shift the equilibrium to the left. Well, we could either remove some reactants or add some products, and that will shift it to the left. So if you add something on one side, so in this case, if we have our reactants and our products, if we add some reactants, it'll shift to the product side. If we remove some reactants, it'll shift toward the reactant side. It'll stay on the same side. It'll shift toward the same side. On the other hand, if we add some products, it will shift to the left toward the reactants, or if we remove some products, it will shift to the right. So we can shift equilibriums back and forth depending on which way. Usually we want to produce more products, that's at least in manufacturing, but you can go either way. So if we have an equilibrium that's in the gaseous phase, one way to change the pressure is to add more, but that would be like changing the concentration. But you can also, we know from our gas laws that if we change the volume of a reaction vessel involving gases, then the pressure will also change. And there can be some effect on equilibrium if there is a change in the total moles of gas present. So if the total number of moles of reactants and products are the same, like if you have 2 gas molecules on the left and 2 on the right, then pressure changes won't affect equilibrium. But if the change in number of gas molecules or the moles of gas molecules are changing, then pressure changes due to volume changes can affect the equilibrium. So let's say the products contain fewer moles of gas than the reactants. So fewer moles would take up less space. So if you reduce the volume of a reaction vessel, by doing that you're going to increase the pressure. In this case, it would favor the products. If the reactants required less volume, meaning it has fewer moles of gaseous molecules, then decreasing the volume would shift it to the left. So it's going to shift. So literally, if you decrease the volume and increase the pressure, you're going to have a shift to the equilibrium to the side with fewer moles of gas. So, and then vice versa, if you increase the volume, the pressure will decrease and it's going to go to the side with more gas molecules. All right, so and it turns out that if the number of moles of gas product equals the number of moles of gas reactant, then the change in volume will have no effect, and so it'll just have no effect. So let's look at this example. Here's the reaction up on top. CO plus 3H2 gives us CH4 plus H2O. You can see here the original equilibrium mixture. Right, it's already settled at equilibrium. Then we are compressing the gases, so we're decreasing the volume, increasing the pressure. And this is before equilibrium is reestablished. So what I want you to notice in the equation, on the right-hand side of the equation, there's 2 molecules of gas. On the left-hand side, there's 4, 3 H's and 1 CO. So 4 on the left, 3 on the right. I'm sorry, 2 on the right. So if you increase the pressure, the equilibrium is going to want to shift to the right to try to decrease the pressure due to the number of molecules. So here you can see in B we compressed it down so that before equilibrium, and then what happens is it allows to get back to equilibrium, and notice that there's 1 more CH4, there's 1 more H2O, and there's fewer, must be 3 fewer H2 and 1 fewer CO. So the equilibrium has shifted to the right to balance out the gas pressure. All right, what happens when temperature is changed for something at equilibrium? Well, Reaction rates generally increase with an increase in temperature. So equilibrium is established sooner, but this doesn't really tell us what happens to the status of the equilibrium. Now, the numerical value of the equilibrium constant will change with temperature, and it will depend on the type of reaction that we have. So, the easiest way to do this is to look to see if heat is a product, which is an exothermic reaction, or if heat is a reactant, which is an endothermic reaction. So in order to know the effect of temperature on an equilibrium, you have to know if it's endo or exothermic. So we can see that increasing temperature is analogous to adding more product if it's exothermic, because heat is a product, or adding more reactant if the reaction is endothermic. So now you can, so once you know which side the heat is on, whether it's exo on the right or endo on the left, if you increase the temperature, it shifts away from that side. If you decrease the temperature, so basically you're removing heat, it will shift toward that same side. So it's the same as if heat were a physical entity, like changing the concentration. You're changing the concentration of either a reactant or a product. So for example, what if you have an exothermic reaction? Now don't forget, exo and endo can't change. It just is what it is. But if you're told it's an exothermic reaction, or if you're told delta H is negative, then you know heat is a product. So what happens if you increase the temperature? Well, if you increase the temperature, it's the same thing as adding a product, so it will shift to the left. If you decrease the temperature, if you cool it down, that would be like removing a product, so it will shift to the right. Now, heat, or delta H, does not appear in the equilibrium constant expression. So actually what happens is that the value for K decreases if you change the temperature. If you increase the temperature, the K value will decrease. And so that's what's happening here. But you can always tell which way it shifts by whether the heat is a product or a reactant. So in this example, heat is a reactant because it's an endothermic reaction, or delta H is positive. So in this case, increase in the temperature would be analogous to adding more reactant, which means it will shift to the right and create more products. So this is one way. If you have an endothermic reaction, you can create more products by increasing the temperature. Of course, if you decrease the temperature, it will shift toward the left. Increasing the temperature would be the same as increasing the Kc for an endothermic reaction, and so that's what happens. All right, so in summary, if you have an endothermic reaction, products will be increased if you increase the temperature. For an exothermic reaction, reactants will increase if you increase the temperature. It'll shift toward the reactants. All right, what does a catalyst do to the, if you add a catalyst to something at equilibrium? Well, a catalyst is something that increases the rate of a reaction but is not consumed by it, as we saw. So a catalyst actually has no effect on where the equilibrium lies. It just helps you get to equilibrium faster. So a catalyst really just speeds up the attainment of equilibrium, and it won't affect the location of equilibrium at all. All right, so let's just look at some examples. All right, in this reaction, N2 plus 3H2 gives us 2NH3, which is an exothermic reaction. What will happen if you increase the pressure? Okay, well, increasing the pressure means, and that would be from changing volume. So increasing the pressure means it's going to want to go to the side with fewer gas molecules. Well, there's only 2 on the right, 3 on the left, so it should shift to the right. Okay, so shift to the right. What happens if you increase the H2 concentration? Well, increasing the H2 concentration is adding a reactant. It will try to shift away from that side, and so it will go to the right. Increasing the T. Well, if you increase the temperature, first you have to decide, is it exothermic or endothermic? So exothermic, that means heat is a product. So if you increase a product, it's going to shift to the left. If you remove NH3, removing NH3, which is again a product, if you remove it, it will shift toward that side, so it will shift to the right. All right, here's one more example. PCl5 gives us PCl3 plus Cl2, and delta H is positive 87.9. So delta H being positive means it's an endothermic reaction. So what will happen if you decrease the chloride concentration? Okay, well, if you decrease the chloride concentration, since chloride is a product and you decrease it, it should shift to the right. If you increase the pressure, increasing the pressure means shifting to the side with fewer gas molecules, which is the left. Increasing the volume, if you increase the volume, you're decreasing the pressure, which means it will do the opposite, it will shift to the right. What if you decrease the temperature? Well, if you decrease the temperature, it will go toward the side where the heat of reaction is, which is the reactants. It's endothermic. So if you decrease the temperature, it will want to go to the left. Right, so what should you be able to do in this chapter? You should be able to apply stoichiometry to an equilibrium mixture, meaning, minus x plus 2x, etc. Be able to write an equilibrium constant expression. Obtain the equilibrium constant if you know the composition of all the equilibrium reactants and products. Be able to use the reaction quotient to decide if a reaction is at equilibrium or which way it will shift to get to equilibrium. Be able to find one equilibrium concentration if you know the others and the K value. Be able to solve equilibrium problems of the kind that you know the initial reactants, and you need to find the concentrations of all the products and reactants at equilibrium, which would be sometimes, that would be for solving for x, sometimes needing the quadratic equation. And then apply Le Chatelier's principle to equilibrium expressions.